There's a 1,000,000,000 to 1 chance we're living in base reality.
And there it is. The quote that launched, I think, 1,000 existential crises online.
It really, really did.
Yeah.
That was Elon Musk, of course, speaking at the Code conference a few years back.
Hmm.
And it could completely set the internet on fire.
Mm-hmm.
It has that perfect quality, it sounds like the ultimate dorm room conversation at 3 in the morning.
Totally. The idea that everything we experience, you, me, this studio, the person listening right now.
Yeah, their car, their coffee cup.
It's all just pixels, characters in some massive cosmic video game. It feels like science fiction. It feels like The Matrix.
It does. It feels like something you talk about after watching a sci-fi marathon, not something you discuss in a serious physics lab.
Right.
Exactly. But here's the thing, and this is the specific reason we're doing this deep dive today. We need to strip away all the pop culture. We have to get past the memes and the Reddit threads and the whoa dude hot takes.
Because there's something real underneath it.
There is. Underneath all that hype, there is actual, serious, peer-reviewed academic literature. People are trying to figure this out. It's not just a stoned thought experiment anymore. It's becoming a genuine scientific hypothesis.
That's right. Today is all about moving from that philosophical what if to the hard logic, the statistics, and believe it or not, some new physics research that suggests our universe might actually be, well, a data processing system.
So we aren't just speculating, we're looking at potential evidence.
We are. We have a huge stack of sources to get through to really make sense of this.
Yeah, let's lay it out for everyone. We're going back to the bedrock, the original 2003 philosophical paper by Nick Bostrom that really formalized this whole argument.
The one that started it all, really.
Absolutely, but we're not stopping there. We are looking at a heavy-hitting statistical rebuttal from an astronomer, David Kipping at Columbia. He uses Bayesian analysis to argue that Musk's math is maybe not quite right.
Which is a huge deal. And then we have some fascinating, truly cutting-edge work from a physicist named Melvin Vopson on something he calls infodynamics.
This stuff is wild. It suggests the universe is literally optimizing itself like a computer algorithm to, save bandwidth?
Something like that, yeah. It's mind-bending stuff.
And on top of all that, we've pulled insights from the Stanford Encyclopedia of Philosophy. We've got takes from Neil deGrasse Tyson, Lisa Randall, and more. So the mission for us today is, it's simple, but it's heavy. Are we NPCs? Are we non-player characters in a simulation? Or are we flesh and blood living in the one true base reality?
It might be the biggest question you can possibly ask. It redefines everything about what it means to be alive.
It really does. So let's unpack this.
To really understand why serious scientists, people with PhDs and tenure, are even willing to entertain this idea, we have to start at the foundation. We have to go back to 2003, to Oxford University, and a philosopher named Nick Bostrom.
This paper is legendary. It's cited everywhere.
It is. Bostrom published this paper, Are You Living in a Computer Simulation? And it just completely changed the landscape of the discussion. Before him, this was pretty much the domain of sci-fi writers,
Philip K. Dick territory.
Exactly. Bostrom turned it into a formal logical argument. He didn't just throw a cool idea at the wall, he built a trap.
A logic trap. I like that phrasing. But to even step into that trap, we have to agree on some ground rules first, right?
Correct.
Yeah.
You have to buy into the premise. Bostrom constructs what he calls a trilemma, 3 propositions where one must be true. But before we get to those, we have to accept a fundamental assumption. If you don't accept this, the whole thing just falls apart.
Okay, what is it?
It's what philosophers of mind call substrate independence.
Substrate independence. Okay, it sounds like a flooring term or maybe something from a construction site. This glue is substrate independent.
It does sound a bit industrial, doesn't it? But in this context, the substrate is the physical stuff your brain is made of. The wet, carbon-based biological neurons, the gray matter. Substrate independence is the idea that mental states, so consciousness, the feeling of pain, joy, the smell of coffee, the feeling of falling in love, they don't necessarily require that specific biological tissue to exist.
So the argument is that the mind is basically software.
That's the perfect analogy. This is the functionalist view of the mind. It says that what makes a brain isn't the fat and the protein it's made of, it's the pattern of information processing. It's the architecture, it's the flow of data.
Okay, that makes sense. Software can run on a Mac, it can run on a PC, you can run on a giant server farm in a warehouse. The software itself doesn't care about the hardware as long as that hardware can execute the code.
Precisely. Microsoft Word is Microsoft Word, whether it's running on a Dell or an Apple. So Bostrom argues that if you could build a computer architecture that mimicked the brain perfectly,
And I mean perfectly.
right, replicating every neuron, every synapse, every electrical impulse, every single neurotransmitter exchange, then the software of consciousness would just boot up on that silicon just as well as it runs on meat.
This is a huge assumption, though. Let's be clear about that. We don't actually know if consciousness is computable. That's still the hard problem of consciousness.
It's absolutely an assumption, and it's the biggest one he makes. If consciousness requires some, specific quantum effect that only happens in biological microtubules, for example, then substrate independence fails. The whole argument stops right there.
But Bostrom is asking us to look at the trend.
He is. Look at the trajectory of our technology. We build artificial hearts. We build cochlear implants that translate digital signals directly into sounds the brain can understand. We're linking brains to computers right now with things like Neuralink. He's just asking us to extrapolate that trend to the whole brain.
Okay, so let's grant him that. For the sake of the argument, let's say consciousness is theoretically computable. Where do we go from there?
Well, the next step is looking at computing power, because simulating a single human brain seems impossibly hard. Like you said, it's the most complex object we know of in the universe.
It is hard for us right now with our tech.
Exactly. But this is where the timeline comes in. Bostrom asks us not to look at our computers today, not your laptop, not even the world's biggest supercomputer. He wants us to imagine a post-human civilization.
Define post-human in this context. Are we talking about cyborgs downloading our consciousness? What is that?
We're talking about a civilization that has reached a level of technological maturity where they have harnessed a significant portion of the total computing power that is allowed by the laws of physics.
So they're not limited by silicon wafers or battery life?
Not at all. They are engineering at the absolute limits of matter and energy. They had maybe thousands or even millions of years to perfect their technology.
And the numbers here, they start to break your brain a little bit.
They're completely astronomical. Bostrom talks about planetary mass computers. Imagine converting the entire mass of a planet, every rock, every drop of magma, every grain of sand into a giant computing substrate.
Or the even crazier idea of matryoshka brains.
Yes, that concept is it's wild. Conceptually, it's a series of concentric Dyson spheres built around a star.
So you capture the entire energy output of the sun, every single photon.
Every photon. And you use it all to drive computation. You effectively turn a star into a CPU.
Okay, so we are not talking about a really fast gaming PC with a good graphics card here. We're talking about something on a scale that is almost impossible to imagine.
We are. And based on something called the Landauer limit, which is the theoretical physical limit of how little energy you need to process one bit of information, Bostrom estimates that a single computer like that could perform something like 1042 operations per second.
10 to the power of 42. That's a 1 with 42 zeros after it. I mean, that number is so big, it's basically meaningless to us.
It is, but let's try to put it in perspective. Neuroscientists estimate that to simulate one human brain down to the full neuronal level would take maybe 1014 to 1016 operations per second.
Okay, so let's do the math there. 1042 versus 1016, the gap is just, it's immense.
Immense. A single one of these post-human computers could simulate the entire mental history of humankind. Every thought, every feeling, every human who has ever lived, from the Stone Age until now. And it would use less than 1/millionth of its processing power for 1 second.
Okay, that is incredibly humbling. It really makes you realize how inefficient our biology actually is compared to what physics theoretically allows. We are running on very, very old hardware.
It really is. And all of this massive computing power just sets the stage for the trilemma.
The logic trap.
The logic trap. Bostrom argues that because this computing power is theoretically possible, and because consciousness is, he assumes, substrate independent, then one of three things must be true. Not might be true, one of them has to be the case.
Okay, let's walk through them carefully. What is proposition number 1?
Proposition 1. The fraction of human-level civilizations that reach a post-human stage is very close to zero.
In other words, we go extinct.
Essentially, yes. This is the doom hypothesis. It implies there's a great filter somewhere in our future. As civilizations get advanced enough to build these incredible computers, they inevitably destroy themselves first.
Which, I mean, you look at the news and that doesn't seem so far-fetched.
Not at all. Nuclear war, engineered pandemics, AI going rogue, nanotech gray goo that eats the entire biosphere. climate collapse. The list is long. The more power we get, the easier it is to accidentally hit the delete button on our own species.
Or maybe technology just inherently becomes uncontrollable at a certain point.
It could. So if Proposition 1 is true, then nobody ever gets the tech to run the simulations because they all die out first. So the good news is we aren't in a simulation. The bad news is we're the Walking Dead. We're just waiting for the filter to hit us.
Okay, that's a pretty depressing option. I don't like that one. What's proposition number 2?
Proposition 2. The fraction of post-human civilizations that are interested in running ancestor simulations is very close to 0.
And ancestor simulations, that's what we would be, right? A simulation of their own past.
Yes. It's the idea that a future post-human civilization would run simulations of their own evolutionary history, maybe for research, for sociology, for art, or even just for entertainment. Proposition 2 says, maybe they can do it, they have the Matryoshka brains, they've got the power, but they just don't want to.
But why wouldn't they? I mean, look at us. We are obsessed with simulation. We play The Sims. We play Civilization. We play Grand Theft Auto. We seem to have this innate desire to simulate worlds and recreate reality.
I know, it seems strange to us. But Bostrom suggests a few reasons. Maybe post-human civilizations converge on a certain set of values where doing this is banned. Maybe it's considered profoundly unethical to create conscious beings who are capable of suffering.
And let's be honest, there is a lot of suffering in human history. Wars, plagues, famine, heartbreak. If you are the one who creates a simulation where all that happens, you are directly responsible for that pain. You are the God allowing all that suffering.
Precisely. If they are hyper-moral, they might just ban it outright. Or, another possibility, maybe they're just so advanced that simulating us would be boring.
Like us watching an ant farm.
Exactly. It would be like us staring at an ant farm for 1,000 years. They might have moved on to pleasures and interests and forms of art that we can't even begin to comprehend. We might just be too primitive to be interesting to them anymore.
Okay, so option 1 is we die before we get the tech. Option 2 is we get the tech, but we lose our curiosity or we develop strict ethical bans against it. Which leaves us with proposition number 3.
Proposition 3. The fraction of all people with our kind of experiences that are living in a simulation is very close to 1.
Meaning almost 100%.
Here's the logic. If they don't go extinct, so Proposition 1 is false, and they do run simulations because they're interested, so Proposition 2 is false, then the number of simulated people will vastly, vastly outnumber the real biological people.
Because one real civilization can run billions of simulations.
Or trillions. Or more. Let's do a simple example. Imagine one base reality civilization that has had, say, 100 billion humans live throughout its entire history. But that one civilization runs 1 million different ancestor simulations, and each of those also contains 100 billion humans.
So you have $100 text billion times 1 text million simulated minds.
Right. Which is 100 trillion simulated minds. So the ratio of simulated minds to biological minds is 1 million to 1.
Okay.
So if you are a conscious entity and you wake up one morning having human experiences, you have to ask yourself a purely statistical question. Am I one of the lucky 100 billion in the one base reality, or am I one of the 100 trillion in the code?
Statistically, you are almost certainly in one of the simulations.
That is the trap. If you reject that we're doomed and you reject that advanced beings lose all curiosity, then logic forces you to accept that we are, in all likelihood, Sims. It's unavoidable.
It is a compelling argument. It's really elegant logic. But before we just accept our fate as lines of code, I think we should pivot to what we actually mean when we say simulation.
Yeah, that's a great point.
Because I think when listeners hear that word, they're picturing Keanu Reeves in a pot of goo, or they're picturing a desktop computer running a video game. But the Stanford Encyclopedia of Philosophy gives us some more nuance on this.
It does, and this is really important because simulation is a scientific term, not just a gaming term. In science, for example, we often distinguish between equation-based simulations and agent-based simulation.
Okay, break that down for us. What's an equation-based simulation?
Think of a weather forecast. Meteorologists use massive supercomputers to simulate the entire atmosphere of the Earth. They have these huge global equations describing fluid dynamics, pressure, temperature gradients. They're calculating how entire fields of data change over time.
But they're not simulating every single water molecule as an individual character.
Exactly. They aren't tracking Bob the water molecule and seeing where he goes. They are simulating the high-level behavior of the system using high-level math.
Okay, and agent-based?
Agent-based is much more like The Sims or SimCity, but on a scientific level. You simulate individual actors, agents, who have their own rules, their own internal states, and their own decision-making processes. Then you just let them interact and see what complex behavior emerges from those simple rules.
So if Bostrom is right, we are likely in an extremely high-fidelity, agent-based simulation. We are the agents.
Correct. And our internal states, our thoughts, our feelings, our consciousness are part of the agent's code.
The Stanford source also brought up this really cool analogy of the dumb hole. This actually blew my mind a little bit because it kind of bridges the gap between digital and physical simulation.
Yes, this is a fantastic example from physics. So scientists want to study black holes, but black holes are light years away. They're invisible and they, destroy everything that gets near them. They're very hard to study directly.
So what do?
They create an analog in a lab. They use fluids, specifically something called a Bose-Einstein condensate, and they set up a flow of this fluid that moves faster than the speed of sound within that fluid.
Wait, so the sound waves themselves can't escape the flow?
Exactly. Just like light can't escape the intense gravity of a black hole, sound waves can't escape the current of this super fast fluid. They call it a dumb hole. Dumb as in mute or silent. The sound is trapped.
And by studying this fluid in a lab, they can learn about actual black holes out in space.
Yes. They can study things analogous to Hawking radiation. They use one physical system, the fluid, to simulate the behavior of a completely different physical system, the black hole. It shows that a simulation doesn't have to just be digital code on a screen. It can be about one system mimicking the relationships and behaviors of another to gain knowledge.
So taking that back to the big picture.
Yeah.
Our entire universe might not be code in the sense of C++ or Python. We could be a dumb hole experiment for some higher dimension.
Theoretically, yes. We could be a physical model being run to test out some string theory parameters. The hardware might be some exotic five-dimensional matter, and we are just the flow patterns happening inside of it.
That feels slightly more dignified than being a video game character, I have to say.
It does. One other thing that really stood out to me in that definition section was this idea of fictions in modeling. The source mentions something called silogen atoms.
This is fascinating, and it's a peek into how scientists actually have to build simulations in the real world. In materials science, let's say you're modeling a tiny crack forming in a piece of silicon. You have a big problem.
Okay, what's the problem?
Scale. You need to use quantum mechanics to describe the atoms right at the very tip of the crack, because that's where the atomic bonds are actually breaking. That requires immense computing power. But for the millions of atoms away from the crack, they're just sitting there vibrating. You don't need quantum math for them. Simple classical physics works just fine.
So you have two different sets of physics that have to interact with each other in the same simulation.
Right. And to make them talk to each other without the whole thing crashing, scientists have to cheat. They create a fiction, a fake atom called a silogen atom. It's designed to have properties of both silicon and hydrogen.
It's an interface, a translation layer.
It's a patch. It's a hack. They place these fake atoms at the boundary between the quantum zone and the classical zone to make the math glue together smoothly. It's a good enough approximation to make the simulation run without needing a supercomputer the size of the sun.
This raises a huge question then. Does our universe have silogen atoms? Does our reality have fictions in its physics?
We might. We often talk about things like physical constants or the absolute limit of the speed of light, or the way quantum wave functions collapse when measured. Could these be the fictions or the artificial viscosity used by a simulator to make our universe computationally feasible?
So if we look closely enough at the edges of reality, do we see the seams? Do we see where the developers used a hack to make the code run faster?
That is exactly what some physicists are now starting to look for.
That is a perfect segue, because if we are going to look for evidence, we need to look at the math and the physics. And importantly, we need to talk about the rebuttal, because not everyone agrees with Elon Musk that it's a 1,000,000,000 chance.
No, not at all. And this is where we have to introduce David Kipping. He's an astronomer at Columbia University, and he published a really significant paper in the journal Universe where he applies Bayesian analysis to Bostrom's argument.
Okay, we need to explain Bayesian analysis. How is that different from the way Musk was counting?
Musk's argument, billions of sims, one real world, therefore billions to one odds. That's what we call frequentist probability. It's intuitive. It's like counting gumballs in a jar. If there are 1 billion red gumballs and one blue one, and you reach in and pick one, it's probably going to be red.
That seems pretty straightforward, so why is it wrong?
It's not necessarily wrong, but it's based on a big assumption. It assumes the red gumballs exist in the first place. It assumes that post-human civilizations actually do create these billions of simulations. But we don't know that. That is an assumption masquerading as a fact.
So what does Bayesian analysis do differently?
Bayesian statistics is all about updating your beliefs based on new evidence. It requires you to start with a prior, an initial belief based only on what you currently know for sure, and then you only update it when you get new information. It deals with deep uncertainty much better. It forces you to check your assumptions at the door.
And what is our prior here? What do we know for sure right now?
We know that we exist. That's one data point. And we know that we have not yet created a simulation capable of hosting a conscious mind. We have SimCity, but the people in SimCity don't know they're in a city. They don't have subjective experiences.
Kipping introduces a great term here that I had never heard before, nulliparous.
Yeah, it comes from biology. A nulliparous organism is one that has produced no offspring. Kipping applies this to civilizations. A nulliparous civilization is one that has not yet created any simulations.
And that's us right now.
That is us. As of today, humanity is nulliparous. We have zero evidence that any civilization, anywhere, has ever successfully created a consciousness-hosting simulation. It's still just a theory.
So how does that fact completely change the math?
Well, Kipping argues that because we are nulliparous, we can't just assign a high probability to the idea that everyone else out there is cranking out simulations left and right. We have no data. So we have to apply something called the principle of indifference. Since we have no data on how common simulations are, we have to start by assigning equal weight to the possibilities.
So instead of billions to one in favor of being a sim,
Yeah.
what does the math actually boil down to?
It drops dramatically. It comes down to roughly 50-50. Kipping calculation actually suggests it's slightly less than 50% that we are simulated. The odds slightly favor the physical hypothesis that we're real, simply because creating a universe simulation is, as of now, a technically unproven technology.
So we went from definitely a sim to a coin flip, maybe, maybe not.
Currently, yes, but, and this is a massive but, Kipping points out a game changer. There is a condition that flips the math instantly and dramatically.
I love a good twist. What is it?
The moment humanity creates one successful ancestor simulation. The moment we hit run on a supercomputer and a conscious entity wakes up inside of it, thinking it's a real human living in the past.
The moment we stop being nulliparous.
Exactly. The moment we become paris reproductive. The moment we become parents to a new digital reality.
And the math just changes.
Instantly. Because at that moment, we have proven that the technology is possible. And if it's possible for us, it was almost certainly possible for any civilization that came before us. The great filter of technical impossibility disappears from the equation. We prove that making simulations is a natural part of a civilization's technological development.
So if we succeed in building the matrix, we basically prove that we are living in the matrix.
That is the paradox.
Yep.
Kipping's math shows that if we develop this simulation technology, the probability that we ourselves are in a simulation collapses to near certainty.
That is terrifyingly poetic. By becoming the gods of a new simulation, we prove that we are just creations in someone else's.
It suggests that this whole race to build the metaverse, or artificial general intelligence, is actually, in a way, a race to debunk our own reality.
We are racing toward our own existential demotion.
That's one way to put it, yeah.
Okay, so statistics says it's about 50-50 for now. Logic says it's likely, but what does physics say? Because you can argue logic all day, but physics is about what we can actually measure. This brings us to the most recent and arguably the most mind-bending research in our stack today, Melvin Vopson and infodynamics.
This is brand new research, published in AIP Advances. Vopson is a physicist at the University of Portsmouth, and he's proposing something really revolutionary, that information isn't just abstract data. He thinks it is a physical form of matter.
We've all heard of mass-energy equivalents. You know, Einstein, Woody Hem C22.
Right. Vopson is suggesting we need to add a third term to that famous equation, mass-energy information equivalence. And he builds it on a principle from the 1960s.
Landauer's principle. Explain that for us.
Rolf Landauer was a physicist at IBM, and he proved mathematically that erasing information is a physical act that must generate a tiny amount of heat. So if you wipe a hard drive, you have to release a small amount of energy into the environment. This creates a direct physical link between abstract bits of data and physical energy.
So information isn't just a concept, it has a physical cost. It's real.
Exactly. And from this foundation, Vopson derives what he calls the second law of infodynamics.
And this plays off the very famous second law of thermodynamics.
Correct. The second law of thermodynamics, which is one of the most bedrock laws in all of physics, says that entropy, which is a measure of disorder, in a closed physical system always increases or stays the same.
Things break down, coffee gets cold, buildings crumble, you can't unscramble an egg, order naturally decays into chaos.
Exactly. But Vopson found something completely different, maybe even opposite, happening with information. He argues that information entropy, which is a measure of randomness or surprise in a set of data, tends to decrease or stay constant over time.
Wait, so physical chaos always increases, but information chaos always decreases.
That's the proposal. The system tends toward cleaner, simpler, more ordered, more predictable information states. And that behavior-minimizing information entropy looks exactly like something we do in computer science every single day.
It looks like data compression.
It looks like code optimization. If you were writing a huge program, you want to delete junk data. You want to compress your files. You want to make it run as efficiently as possible. Vopson is arguing the entire universe is behaving exactly like a computer that's trying to save bandwidth.
That is a wild claim. I mean, does he have any evidence for this?
He provides 4 main pillars of evidence. The first one is digital storage itself, where we see data degrades over time, reducing its entropy. That's expected. But the second one?
The second one is a bombshell. It's about genetics.
He looked at the COVID-19 mutations, right? He did. Vopson analyzed the mutations of the SARS-CoV-2 virus as it evolved. Now, standard Darwinian evolution says mutations are random errors. They're just mistakes in the copying process. Some happen to help the virus survive, some don't. But the source of the change is random noise.
But Vopson found a pattern in that noise.
A very clear one. He calculated the information entropy of the virus's RNA sequence as it mutated from the original strain to alpha, then delta, then omicron, and he found that the information entropy consistently decreased with each major variant.
Meaning the code was getting simpler or more predictable?
It was getting more optimized. It wasn't just changing randomly, it was actively shedding information weight. It was becoming more compressed.
He also mentions an older experiment from 1972 by Spiegelman, doesn't he?
Yes, Spiegelman's monster. This is a classic experiment.
Yeah.
Spiegelman took an RNA virus and put it in a test tube with everything it needed to replicate, but with no cells to infect. He just let it copy itself over and over again.
So what happened?
Over 74 generations, the virus evolved. It ditched every single gene it didn't strictly need for replication. It shrank its genome by 95%. It became this tiny, hyper-efficient little strip of replicating code.
It stripped out all the bloatware.
It absolutely did. And Vopson argues this isn't just biology, it's the second law of infodynamics at work. The code is optimizing itself for the hardware it's running on.
That is spooky. It really does sound like a software update. Okay, so what's the third pillar of evidence?
The third pillar is even more fundamental. It's atomic physics, specifically something called Hund's rule.
Oh, wow. This takes me back to high school chemistry. Electron shells.
Exactly.
Yeah.
Electrons orbit an atom's nucleus in shells, the SPD and F orbitals. And we've known how they fill those shells since 1927, thanks to a guy named Friedrich Hund. They don't just pile in randomly. They space themselves out in a very specific, predictable pattern.
But we haven't really known why they prefer that pattern.
We knew it was the configuration of lowest energy. But Vopson decided to calculate the information entropy for the electrons in all their possible arrangements. And it turns out, the way electrons actually arrange themselves in an atom is the exact configuration that minimizes their information entropy.
So an atom is structured to hold the least amount of data possible to describe its state.
Correct. Of all the ways it could be, it chooses the path of least data. Vopson argues this is evidence that the fundamental building blocks of matter are themselves optimized for data storage.
Wow, okay. And the fourth pillar?
The fourth pillar is symmetry. The universe seems to be obsessed with symmetry. Snowflakes, starfish, flowers, our faces, the orbits of planets. Why?
I don't know, because it's pretty, because it's stable.
Vopson argues it's because it's efficient. He argues that high symmetry corresponds directly to low information content.
Explain that. That's not immediately obvious.
Think about describing a shape to a computer. If I want to describe a totally random, squiggly blob, I have to give the computer the coordinates of every single point on its perimeter. That's a lot of data.
Okay. But if you want to describe a perfect square...
I just say 4 equal sides, 90-degree angles, side length of 2.
Yeah.
Done. That's very little data.
I see. So symmetry is a form of data compression.
Exactly. Vopson argues the universe prefers symmetrical states and shapes because it is the most efficient way to render reality. It saves processing power.
So if this all holds up, and the universe is a simulation, then the fundamental laws of physics, evolution, atomic structure, symmetry, they're basically just very clever compression algorithms.
That is the argument. The entire universe is designed to run on as few bits as possible.
This leads us to the part of this whole thing that feels the most like science fiction, but again, is rooted in some hard research. If this is a simulation, and if it's optimizing to save resources, it implies there are limits.
Every computer has limits.
Sure.
A maximum CPU speed, a finite amount of RAM, a screen resolution. Even a Matryoshka brain would have a max clock speed.
And if there are limits, scientists should be able to find them. They are literally looking for the pixels. They are looking for the screen door effect on the universe.
This takes us to the research by people like Silas Bean and Zora Davuti, which was covered in that Space.com article.
So if you run a numerical simulation on a computer like scientists do for lattice QCD, which simulates quarks and gluons, you can't have infinite continuous space. Computers can't handle infinity.
Right, you have to chop space up into a grid, a lattice. Imagine a giant 3D chessboard. Points in space are only defined at the intersections of the grid lines.
And a grid, by its nature, implies a specific geometry. It has direction.
It does. And this is the absolute key. In a continuous, smooth universe, like the one we think we live in, physics should look exactly the same no matter which direction you look. It should be isotropic.
But in a grid.
In a grid, moving straight along the grid lines, up, down, left, right, is fundamentally different than moving diagonally across the squares. The math is different. This is called rotational symmetry breaking. Things look different depending on the direction.
But how could we ever possibly see that on a cosmic scale? The grid would have to be unimaginably tiny.
Cosmic rays. These are the highest energy particles in the universe, and they're traveling across the cosmos at very close to the speed of light. Zora Davuti from MIT proposed that if space is pixelated, these cosmic rays should show a specific distortion in their energy spectrum, depending on the direction they came from.
So if we see that cosmic rays from, say, the north have a slightly different maximum energy than cosmic rays from the northeast, we might actually be seeing the grid lines of the simulation.
Theoretically, yes.
Yeah.
That's the test. We haven't found definitive proof yet. Our detectors might not be sensitive enough, but the methodology is sound. We are looking for the aliasing artifacts of the universe's rendering engine.
But there's another potential glitch that is even stranger. This one involves a physicist named James Gates, a theoretical physicist at the University of Maryland who works on superstring theory.
This is the error-correcting code discovery. This one genuinely shocked the physics community when it came out.
So Gates was just analyzing the math of supersymmetry. These are the incredibly complex equations that describe the fundamental particles of the universe. He wasn't looking for computer code.
No, he was just doing the math. But deep inside these fundamental equations, he found these structures called adinkras. And when he analyzed them, he realized they were mathematically identical to something called doubly even self-dual linear binary error-correcting block codes.
Okay, that is a mouthful. Translate that for those of us who aren't theoretical physicists working on string theory.
It's the same type of code that your web browser uses. When you download a picture, the data gets chopped up into packets and sent over the internet. Sometimes bits get flipped, there's static on the line, an error. Error-correcting code is extra data that's embedded in the signal that allows your computer to check for those errors and automatically fix them on the fly.
So you're telling me that embedded in the fundamental laws of reality, we found a checksum, a spell checker for physics?
Essentially, yes. Gates himself found code that is designed to check for transmission errors. He famously asked the question, how did computer code get into the equations of physics that describe the universe?
Now, a skeptic might say that math is just math and patterns repeat themselves everywhere.
True. It could be a massive coincidence, but it's a very, very suspicious coincidence if you happen to be looking for evidence of a computed reality. Why would the fabric of the universe need error correction unless it was being transmitted or processed as data?
Then there's the big one, the measurement problem in quantum mechanics. We can't talk about simulations without talking about the observer effect.
Rich Terrell from NASA's Jet Propulsion Laboratory is a big proponent of this argument. In quantum mechanics, we know that subatomic particles don't have a definite state. They don't have a specific position or velocity until they are measured.
Until you look at them, they're just a fuzzy wave of probability.
Exactly. The classic Schrödinger's cat scenario. The cat is both dead and alive at the same time until you open the box and look. Terrell compares this directly to how a modern video game works.
Right, think about a huge open-world game like Grand Theft Auto or Cyberpunk. The console doesn't render the entire city all at once down to every last brick. that would melt the processor.
It relies on something called frustum culling. It only renders what the player's camera can see. The street behind you, it doesn't exist as pixels, it's just data in the RAM. It only becomes real when you turn your character around to look at it.
And Terrell is arguing that quantum mechanics looks suspiciously like a cosmic optimization engine. Matter is only rendered into a definite state when a conscious observer, a player, looks at it.
It connects right back to Vobson's work. Why waste the processing power rendering an atom if no one is looking at it? The inherent weirdness of quantum mechanics might just be the system conserving memory and CPU cycles.
It all keeps coming back to efficiency and optimization, which, believe it or not, actually brings us to cosmology and the expanding universe.
This is another really interesting connection that Vobson makes in his paper. We have something of an entropic paradox in cosmology.
Okay, walk us through that one.
We know the universe is expanding. And based on the second law of thermodynamics, the total physical entropy, the disorder of the universe, should be constantly increasing as it expands and cools. But we also generally assume the universe is a closed system, where fundamental properties like total energy are conserved.
So how do you balance the books? If one thing is going up, something else has to be going down.
Vobson suggests that if the total entropy of the universe needs to stay constant to satisfy conservation laws, but the physical entropy is rising because of the expansion, then something else must be falling to compensate.
Let me guess. Information entropy.
You got it. He argues the information entropy must be falling to balance the rising physical entropy.
The universe is constantly balancing its data budget.
That's a great way to put it. The expansion of the universe might be the very mechanism that allows for the increase in physical complexity. Us, stars, galaxies, by paying for it with information optimization. It suggests the universe is a closed system managing a finite resource, just like a computer.
Okay, so we have logic, we have math, we have physics, and now cosmology, all pointing in this very strange direction. But let's step back for a second and ask the very human questions. Why? Why would anyone simulate us?
This is where we have to enter the realm of speculation, but it's informed speculation. Bostrom's original paper focused on ancestor simulations.
So basically, a history class for a future civilization.
Essentially. They're trying to understand how they got to where they are. They might ask, how did our species survive the tumultuous 21st century without nuking ourselves? They run the sim 1,000 times to find out the most probable answer.
But the Stanford source and others suggest different motives, right?
Absolutely. Maybe it's not about history. Maybe it's a pure science experiment. Maybe we are a dumb hole model for sociology or evolution. Or maybe it's Elon Musk's theory. It's just a game.
Entertainment, The Sims, Planetary Edition.
His quote was, "Games will become indistinguishable from reality." If that's true, why wouldn't people play them? Maybe you chose to play the podcaster character. Maybe I chose the expert. Maybe the listener chose their specific role in this grand open world game.
But there are very loud skeptics. We have to bring in Lisa Randall from Harvard. She's not buying any of this.
No, she is very, very skeptical. Her main argument is essentially, get over yourself. She calls it the ultimate form of hubris.
That feels like a solid burn on all of humanity.
It is. She asks, why would a godlike advanced civilization simulate us? We are a messy, primitive, often violent species on a random rock orbiting a nondescript star. Are we really interesting enough to warrant the massive computational cost of simulating our individual consciousness?
Yeah, that's a fair point. Maybe we aren't the main characters at all. Maybe we're just the background NPCs in a simulation that's really about, I don't know, the life cycle of beetles or the evolution of bacteria.
Exactly. And Max Tegmark from MIT adds another important layer of skepticism. He says, sure, it's logically possible, but if we are in a simulation, we have absolutely no clue what the real laws of physics are in the universe outside our own.
Right. We are just studying the game physics. We don't know what the computer itself is made of.
We might be meticulously studying the code of Mario Kart and thinking we're understanding the silicon architecture of the Nintendo Switch. Tegmark says this makes the hypothesis almost unscientific because it cuts us off from fundamental reality. We hit a wall that we can never ever see past.
You know, there's also this weird theological parallel that Bostrom himself points out at the end of his paper.
It is really hard to miss.
Yeah.
If the simulation hypothesis is true, you have a creator.
Someone who pressed the run button.
This creator is, for all intents and purposes, omnipotent. They can change the laws of physics, the code, at will. They could pause the sun, they could delete gravity if they wanted to.
They're also omniscient.
They can monitor the state of every processor in the system, which means they can read your thoughts. Your brain states are just data to them.
And they created our entire world.
And as Bostrom notes, there is even a plausible mechanism for an afterlife.
How so?
Well, you are data. When your character dies in the simulation, your data doesn't have to be deleted. It could be saved to a hard drive. It could be paused. It could be re-uploaded into a brand new simulation.
Reincarnation via copy-paste.
Precisely. It turns some of the deepest religious questions into essentially a computer science problem. It's fascinating how these hyper-rational scientific arguments end up looping all the way back to some of our most ancient spiritual concepts.
So after all of that, where does this leave us? We have covered a massive amount of ground today.
We have, let's try to sum it up, we have Bostrom's logic, which suggests that statistically, it's likely we're Sims unless we're either doomed or future civilizations are incredibly boring. We have Kipping's statistics, which says it's more like 50-50, but we hold the swing vote based on whether we create our own Sims.
And then we have Vopson's physics, which suggests the universe behaves suspiciously like a piece of optimizing software, compressing its own data.
Neil deGrasse Tyson had a great analogy for all of this at the Asimov debate a few years ago. He compared it to watching a game of chess.
Oh yeah, I remember this.
He said, imagine you don't know the rules of chess, but you're watching the pieces move. You might figure out that pawns move forward and bishops move diagonally. You slowly figure out the laws of physics for the chessboard.
But then, all of a sudden...
But then suddenly, a pawn reaches the other side of the board and becomes a queen.
A promotion. It breaks the rules.
Tyson says that move is freaky. It violates all the rules you thought you knew. He suggests that the really weird things in our universe, quantum entanglement, dark matter, the absolute limit of the speed of light, they might be those freaky chess moves. They're the artifacts of the underlying code that we just don't have the instruction manual for.
It's a humbling thought, but I think I want to end on that provocative thought from Kipping's paper again, because it feels like the most actionable and frankly the most chilling takeaway.
The Paris condition, us becoming creators.
Yes. We are racing to build the metaverse.
Yeah.
We are racing to build artificial general intelligence. We are actively trying to simulate human brains.
And Kippy's math says that the closer we get to succeeding, the closer we get to proving our own unreality.
It's the strangest paradox. Our greatest technological achievement, creating a fully conscious, simulated world, would be the undeniable proof that we are just characters in someone else's great achievement.
The moment we hit run, the probability that we are in base reality just collapses. We look at the screen, see these new simulated beings looking back at us, and realize we are just looking in a mirror.
And if that happens, do the simulators pull the plug? If the Sims figure out they are Sims, is the game over?
That is a risk I suppose we will just have to take.
Well, on that existential bombshell, I think we're going to wrap up this deep dive. Hopefully we didn't use up too much of the universe's processing power today.
If the sky outside suddenly turns purple and the resolution drops, you'll know who to blame.
Thanks for listening, everyone.
Stay curious.
See you in the next simulation. Or, next week. Bye.